Hi, welcome to the analysis design of a flyback, part 12, practical input filters. Okay, I've been away for a while and I haven't done any of these videos, and I recently actually got out of the hospital a few days ago. I had a bout of vertigo. That's where your vision starts spinning. Luckily, got over that. Anyway, I wanted to talk about a practical input filter. I had done video 11 and 12. And let me go up here. In video part 11, I discuss common mode noise and how it's generated. And in part 10, I discussed about the input filter, and I may have gone all the way to part 9, which is the input filter itself. Okay, so I broke it up into basically two main, a differential mode and common mode. Okay, so now here we put both filters together. Okay, and this section. Okay, and what I'll do is I'll put a little green or purple. This part, you can consider it as the differential mode. Noise, and this part would be the common mode. Okay, now one of the ways of distinguishing them, which is which, is all you have to do is look at the dot of the coupled inductor. In this case, if you notice, the dot is on the same side. So you can think of it that if the dot is on a common side, then it would be a common mode choke. So as long as you see that, then you can just by inspection say this is a common mode choke. Now this little Z that I drew in here, that means that it's coupled. In other words, this and these are wound on the same core. Okay, so they interact with each other. Okay, likewise, the differential mode is also coupled as well. So you have a winding on the line side. This would be the line side, which is the hot, and then you have the neutral side, okay, which is considered ground. Okay, so you have a differential mode on top on the line and a differential mode on the neutral. Okay, and they're coupled. Okay, and then you have filters here. Okay, now I want to talk a little bit some of the properties that some of these filters have. Normally, the common mode inductors will be larger than the differential mode. Okay, in this case, I'm going to go ahead and use a spice example, and let me go ahead and make this 10 millihenries. Okay. Can't seem to erase this. Okay. I'll make this. Let's see where the 10 millihenry. Let me make sure that it matches my spice. 10 and 10. Yes. Okay. So it matches. So typically this will be greater than this inductance. Okay. So that's one thing, a property that they usually have. Okay. Another is, if you look very carefully, especially in the common mode area, in this area, you will see what is called a Y cap. Okay. And Y caps work with the common mode inductor to attenuate the common mode noise. Okay. And those you can always tell what they are by where they're grounded. Okay. Now remember, this is your hot and this is your neutral. Okay. And typically you'll have one that is connected to earth ground, or they might even call it a chassis ground. Okay. Well, if you see a capacitor that's connected from one, either the line or the neutral, and then the other is connected to the chassis, those are called Y caps. Okay. And they're used to attenuate the common mode. Okay. So in this schematic, I have them at the input. Okay. Now there's a disadvantage of having them directly at the input, but I'm using this topology because this filter design is from one of the books, I believe is Power Supplies A through Z, and he uses this in his explanation of the filter, so I'm going to go ahead and use his topology. Okay. Now in his, he uses another Y cap not only on the left side of the common mode, he also uses it on the right side. Okay. So if you notice here, this cap is connected to the line and this other side is connected to the earth ground. Okay. So this is also a Y cap. Okay. And as well as this one here, Y cap. Okay, so the function of these 4 caps are to attenuate common mode. Okay, which is okay. And if you have a question, what is common mode, go ahead and view the video prior to this, where I explain where the common mode noise comes from. And typically common noise is switching noise. Usually switching noise from the MOSFETs. Okay. Okay, so now we're back to, or down here to differential. Okay, we already covered this, that it's got a smaller inductance. And then the next one is for X cap. Okay, what is the X cap? And then it says that I have that it works with the DM coil to attenuate DM noise. Okay, so what is that? Okay, so these is your differential mode inductor, and any capacitor that is connected between the the line side and the neutral side, and not the chassis, but just between these two, those are called X caps. Okay, so that would be an X cap, and this can perhaps be considered an X cap. Is more really a damping capacitor, and I'll explain that a little bit further. And I also have another one over here, X cap. Okay. Okay. But these are usually big, or at least the first one to the left, to the right, I believe. Yeah, to the right is usually a big cap. Okay. And what it does is going to filter out differential signals. Okay. Okay. So now let me go back. Okay. That's number 5, which I already said that the X caps are usually larger than the Y caps. That is true. In this case, let me see where I'm at. Okay, CO is 100 microfarad, and this was derived, and I believe in video number 9, calculated what the attenuation was, and I actually set my capacitor as being 100 microfarad, and I solved what kind of inductance I needed to give me the attenuation. So typically the X caps are going to be big. Now if you look at the Y caps, typically they're low values, and most of the ones that I've seen are typically 10 nanofarads. So if you notice, that's 10, that's 10, 10, and 10. So they tend to be small value, typically much smaller value than your differential caps. Okay, and the reason is that they have to limit the amount of leakage current that actually flows through that. Okay, so let me go ahead and maybe analyze it a little bit more. Okay, now when you have this type of a filter, it might look a little bit daunting. Okay, but let's see if we can get a sense of what it does. Okay, now let's go ahead and consider the common mode. Okay, let's say common mode. Okay, and let's see how that looks like. Okay, common mode means that the noise will be coming through both the line and the neutral. Okay, and typically you can think of that as being shorted together. Okay, and if you short those lines together, okay, then what you're doing is you're shorting this cap right there. In other words, if you were to connect the line to the neutral, that shorts across this cap, it shorts across this cap, and it shorts across this cap. Okay, basically you don't have anything. Okay, so let's draw the model. Okay, see if we can see if it makes sense. So in shorting the line, we can say that this is L, and I'll put dash N. Okay, okay. Now here's another thing that you can get from that. If you short this line to this and this line to this, you basically have you're going to have two inductors basically. Okay. Now keep in mind, in the common mode, it's these two lines, the line and the neutral, in respect to earth ground. Okay, so let's go ahead and continue. Okay, this is your earth ground, and if you look at these two, okay, if this line is shorted to this line, that means that these two capacitors are tied in parallel to each other. So basically you have the Y caps are going to be 2, and let's just say 2 Y caps for right now. Okay. And if you look at here, okay, shorting that to this means that these are also in parallel. Okay. So in this case, they're both 10s and they're in parallel. So this is 20 nanofarads. That's 20 nanofarads. Okay. Okay. And like I said, this is out of the equation because it's shorted across. Okay. Now, on the previous video, if you add a signal to both sides and it's a common to both sides, the differential will not be seen by them. They actually look like wires because the flux actually cancels. So if you go ahead and watch video, I believe 10, I explain how they cancel. So basically these are shorts. They're actually shorted across. Okay, and of course this is being shorted. So basically you end up with a model that looks basically like this. Okay. So in this case, you can go ahead and put this back. Okay. And since you short them, you can actually model this with a differential signal. Okay, so let me go ahead and label this a little bit better. Now remember, this is, or 2 lines. This is going to be your, you can consider to be your out, but it's also your ground because you're shorting both lines. In other words, you're shorting this out, and I'm shorting this line, and I'll call this G and D. Okay, so those 2 lines are connected together. Okay, and this line I think I have too many applications opened. Okay. Okay. So that's that. And this is going to be line and the neutral. Okay. And then this is the chassis. Okay. So let's go ahead and take a look at the schematic. Here is line and neutral. They're connected together. And my out and my ground are connected together. Okay. So to test the differential attenuation, what I have to do is I have to tie these together, and then I insert a current source. Okay. Now for simulation purpose, I've added R10 and R9, and the values of those are 1K. Well, I'm sorry, 1T, meaning that's tera ohms. Okay, so basically it's an open. Okay, and I'm adding a signal that is common to both lines, and they travel, and these do not see or do any attenuation of the signal until they actually come to this circuit. Okay, and then from there they're summed, and then it goes to the bus, and it goes through this V common. Okay, so in this case I can feed the signal a current source here, and then I need to monitor what the current would be at the common. So basically that's what this filter is doing. Basically is going to attenuate, is basically it's going to be a low pass filter here. Okay, so before we do any simulations, let's go ahead and see if we can calculate what we should expect. Okay, we know that these are, let me go back just to be sure, it's 10 millihenries, 10 millihenries, and then these are 20, and these are 20. Okay, so since these are in parallel, the total should be should be 5 millihenries. Okay, so then if we try to calculate what the break frequency should be, 2 pi 5 millihenries and times the total capacitance that you have here. So in this case I'll go ahead and put since they're basically in parallel at the low, I'll say that they're 40 farads. Okay, so when you calculate that, 1 divided by 6.28 times, and that's 5 milli times 40 nano, close the parentheses and raise it to the 0.5, close parentheses, and we should get close to 11.2 kilohertz. Yeah, 11.2 kilohertz. Okay, so then we'll go ahead and do the simulation. Okay, here I added the AC 1, that's the magnitude of 1. Okay, and then to plot what the common mode will be, I'll go ahead, let me uncomment this. To uncomment the differential, I'll put a little star, and what I want to do is I want to plot just the current that is going through here. Okay, so go ahead and run, and there you go. Okay, so I calculated a frequency of 11.2 kilohertz. So basically, if you have a switching supply, the switching supplies that I usually design are anywhere from 100 to 200. So if you're switching at 100, you're going to have at least close to an attenuation of 100, or close to negative 40 dB. Okay, and you'll have this type of a response. Okay, so that's the common. Okay, so let's go ahead now. Let's take a look at the differential mode. Okay. Let's see if you can see that as well. Okay. In differential mode, the signal is applied between these two lines. In other words, you would put a signal source and tie it in between here. Okay. And you would measure it differentially. You would measure it right here. Okay. Now, in a differential mode, okay, the common mode has no effect whatsoever, and you can think of them as a short as well. Okay. And since they're basically a short, they have very little effect on the damping, or not the damping, but the attenuation of the differential mode. Okay. Now, if you look in here, you can see that the X caps are connected right across the two lines, the out and ground. Okay, you have that here. Okay. Now, this may be a little bit difficult to see, but if you connect the signal differentially and the earth is not connected to either the hot or the bottom, the hot or the neutral, and is basically isolated, okay, then you can see that this combination, these two X caps, in reality, you can neglect the earth, and you can say that these two capacitors are connected in parallel. Well, I'm sorry, in series. Okay. By the same token, you can say the same comment here, that these also connected in series. Okay. So that simplifies our circuit. And let's see if we can draw the circuit. Okay. So basically you had a Y cap. Okay. And remember, it's connected to Earth, but we're going to go ahead and neglect it. Okay. And then we had, and I'm going to go ahead and just to illustrate that you have the common mode here, but in reality, to the differential mode signal, it looks like a short. And then you have the other two Y caps connected. Okay. Let's see. And then I'm going to connect the three other caps. Okay. Okay. Then I'll connect the differential cap, or the inductors rather. Okay, and let me make sure that there's one there on the left and two on the right. So I'll go ahead and put the X cap right there, and I believe this is a 10 nanofarad. This should be 100. And I believe I had a 440 with the resistor, but the resistor kind of decouples it. Okay. So if this is the case that these are in series, okay, the equivalent of these will be, since this is 10 and 10 and they're equal, so they're basically 5 nanofarads. 5 nanofarads. Okay. So now what you can do is, okay, you can calculate what the corner frequency is going to be. Okay, it's going to be 2 pi. In this case, this is, I believe, 15 microhenry. 15 microhenry. So it would be the sum of both. 15 microhenry times the total cap. Okay, so these are in parallel with this, and that. So basically, these are so small that actually they get swamped out. So you can say, for completeness, we'll go ahead and say that it's 5 nanofarads in parallel with another 5 nanofarads in parallel with the 10 nanofarads in parallel with this one here. And let's try that, see if we get close. We may have to add this depending how small the ESR is. Okay, so we'll have that, and I believe it should be close to 3 kilohertz. Okay, so let's go ahead and do that. And basically these will be 30, and I'm just going to go ahead and multiply it. Assume that this is the dominant. Okay, let's see what kind of frequency we get. 1 divided by excuse me, 6.28, 30 micro times 100 micro 5, and get a frequency of 2.9 kilohertz. 2.9 kilohertz. Okay, so we'll go to the simulator. Okay, and here's the schematic. Now keep in mind that these two models are not this simplified version. This is the simplified common mode, and this is the simplified differential mode. And let me go ahead and write it down that this is the differential mode. Okay. And the reason I left it like that is because I wanted to show that they're exactly the same. Okay. They have the same caps, same, and that in this case, this is the differential mode. Adding the signal differentially between the out and the ground, and I'm measuring differentially. And here I'm connecting the out and the ground together, and I'm injecting the signal through the common mode, okay, where both signals are common to both the out and GND. And then I'm measuring the common mode on this side. Okay, so let me go ahead and comment this one, this SPICE directive. I can comment out by putting a star, and what I want is I want the auto plot of the differential. In other words, I want to see the current going through here. Okay, and it should have a corner frequency of close to 3 kilohertz. So in this case, we can get our go ahead and turn this into color, and I'll put that cursor here, and the 3 dB should be close to where I get 3. Here's a delta of 2.92, which is close enough, and if you look here, it's 2.98. So that's 2.98 kilohertz, which is pretty close to what we calculated. So it's 2.84 kilohertz. Okay. Alrighty. So let's go ahead and plot both at the same time to show that how this integrated common mode and differential mode does two functions. Okay, so here we go. So here we have the differential attenuation. It's a low pass filter. Okay, and it's at about 3 kilohertz. And then you have the common mode, and the common mode is at about 11 kilohertz. Okay, so in a nutshell, this is kind of how a practical differential or practical input filter should work. You should have a common mode and a differential mode. Okay, and it should be straightforward. If you have any questions or any comments, you can please email them to my AOL account. I will post my email down below, and like I said, just if you have any questions, just email me, and provided that I have time, I try to answer most of the questions. Thank you for watching.